Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. This is the 18th and final video of the Lithium Mine to Battery Line series to investigate what Tesla unveiled at Battery Day. The first half of the video is the last 17 videos condensed into one and contains what I consider are the key points. Some of the key points have been refined and clarified, along with more thoughts in some areas like nickel and silicon-doped LFP. But substantively, the information is the same. The second half of the video contains my thoughts on the implications of Battery Day, estimates, projections, and insights after working on the series for 9 months. It starts at the timestamp labeled Implications. You will notice in this video that I have a cold. I would have liked to have waited to record, but the only way I was going to get the 18-page script recorded and the video out on time was to power through it. So apologies in advance for the gravelly voice. Before we begin, a special thanks to my Patreon supporters and YouTube members. All the links to contribute are in the description. If you can't contribute, be sure to like and subscribe because love helps the channel too. Let's get back to the series finale. Tesla assembled their presentation in a slightly haphazard way. For this video, I'm going to reorganize it in a way that makes sense to me. We're going to work from the beginning of the life cycle at the mine and work our way to a finished vehicle. On screen is a high-level overview from mine to vehicle. I've focused on lithium here because we don't know how far upstream Tesla will go with nickel. With that said, we will touch on nickel in this video. Out of everything that was announced at Battery Day, extracting lithium from clay with salt and water attracted the most doubt. In my view, what must be done will be done. If Tesla isn't able to get enough lithium from its suppliers, Tesla will get into lithium clays. As I've shown, Tesla's been cultivating in-house expertise for extracting lithium from clay for at least 5 years, and they've had the desire to bring lithium extraction and production in-house for at least 7 years. The idea of extracting lithium from clay isn't a new idea. In fact, there are dozens of potential processes that have been tested, some of which achieved good yields and are similar to what Tesla proposed at Battery Day. If Tesla chooses the most advanced technology available and combines it with the right clay deposit, it's well within Tesla's reach to extract clay from lithium economically. This is pure speculation, but I think Tesla will have 2 lithium production centers in North America in the late 2020s. This is because lithium concentrates from different sources require different process steps to convert them to hydroxide. First, they'll have a hydroxide plant in Texas that processes lithium concentrates from hard rock sources to feed the Austin cathode factory. Second, they'll have another hydroxide plant at the lithium clay mine to process concentrates from lithium clay along with another cathode factory. What about time frame? We know that there are thousands of lithium claims in Nevada, and Tesla's 10,000 acres could easily be hiding somewhere in those claims. However, either Tesla hasn't progressed to permitting yet, they're partnering with an existing mine, or they're operating under a pseudonym. Regardless, indications are that it would take Tesla at least 5 years to get the mine into production. Given how far upstream the lithium mine is, it would be the least pressing project Tesla unveiled at Battery Day. Tesla will need to establish lithium hydroxide and cathode production first. According to Benchmark Mineral Intelligence, Tesla's hydroxide refinery is expected to begin operations in Q4 2022. If there are enough hard rock sources to feed that hydroxide plant and future hydroxide plants, Tesla may not need the clay mine in Nevada, and it could be a fallback plan. This would make sense because Tesla will probably need cathode material from this cathode plant for the full-scale 4680 lines at Giga Berlin and Giga Austin next year. This leads us to nickel. Elon has stated that nickel is what Tesla needs most. Why is that? Nickel is difficult to mine, and even more difficult to mine in an environmentally friendly way because it's toxic and the common ways to extract it compounds that toxicity. There's been a lot of chatter about nickel projects and Tesla in Asia-Pacific countries such as Indonesia and New Caledonia. The nickel that comes from these mines tends to be laterite ores, and of the types of nickel ores, laterite ores are one of the most difficult to extract in an environmentally friendly way. Unfortunately, most of the newer potential mines are from nickel laterite ore in the Asia Pacific, which is why you're hearing so much about nickel from Asia Pacific countries. The most environmentally friendly option for nickel for North America and Europe by accident of geology would be from North American and European sources. This is because nickel deposits in the northern latitudes tend to be sulfide deposits that are easier to extract in an environmentally friendly way. Note that I'm saying sulfide here rather than sulfate, which are two completely different things. Nickel sulfide is the ore, and nickel sulfate is the finished product that's used in cathodes. There is a massive wildcard here. Tesla is using nickel metal powder instead of nickel sulfate for their cathode factory. This means they may be able to extract the nickel from the laterite ores in Indonesia and New Caledonia in a more environmentally friendly way. But I'm still looking into the chemistry of how this could work. Regardless of whether Tesla can create a better process for the laterite ores in the Asia Pacific, Tesla's use of nickel powder will definitely have benefits for the sulfide ores in North America and Europe. As shown on screen, a typical cathode process turns nickel sulfide ore to an oxide, then a sulfate, and eventually back to an oxide again. As for Tesla's process, the Sharep method noted in the cathode factory video could be used to create nickel metal powder directly from nickel sulfide ore. And then Tesla's cathode reactor and sintering process would convert the metal powder to a finished oxide cathode. Let's do a quick recap on the supply chain before we move on. It may be later this decade before we see Tesla's lithium extraction from clay, but it isn't science fiction and it's entirely feasible. The only reason why Tesla may not get into lithium clay mining is if lithium miners can provide Tesla with enough raw material for their hydroxide plants. My guess is that the cathode plant will be up and running by mid-2022, and the lithium hydroxide plant will be up and running by the end of 2022. There's no sense in having a lithium hydroxide plant if they don't have a cathode plant to dump the lithium hydroxide into. The cathode material will also be needed for ramping 4680 lines in Berlin and Austin. Why is nickel a bottleneck for Tesla? Although there is a huge nickel supply in the world, there isn't enough marginal supply of the right type of nickel that Tesla needs that also satisfies Tesla's environmental requirements. Nickel sulfide ores are more environmentally friendly, but they're in short supply. Nickel laterite ores are plentiful but notoriously dirty. Deep pockets like Tesla's may help with this, and I'm eager to watch it play out. Whether from sulfide or laterite ores, the end product Tesla needs is pure nickel powder instead of the typical nickel sulfate. Nickel powder uses fewer manufacturing steps, which should reduce cost and environmental impact. This brings us to Tesla's cathode production process. Tesla's cathode reactor will likely have near 100% yield rate with zero toxic wastewater. Based on the images from Battery Day, they have a machine already set up that just needs to be reproduced and scaled for their cathode plant. What about the cathode material itself? Let's start with the 12% cost decrease. Tesla made it pretty clear that most of the cathode material savings was due to their in-house cathode production process. This would account for about 10% of the 12% cost reduction. The other 2% was likely due to the removal of cobalt and the slight increase in energy density. Tesla advised that besides the 12% cost savings, the new cathode provides a range increase of 4%. I'm assuming this is due to a slight increase in voltage or potentially a large increase in the cathode's ability to store and release lithium ions, which is called specific capacity. The increase in voltage appears more likely, and from what we saw in the cathode mini-series is entirely possible with a cobalt-free cathode. One thing that's missing from the simplified illustration here is Tesla silicon. I've left Tesla silicon out because as far as I can tell, the process to make Tesla silicon will require very little floor space. It may be as simple as dipping silicon in a solution containing polymer and then drying the silicon. The difficult part, of course, would have been finding the right recipe. I'm expecting that the bulk of the material that goes into the anode will still be graphite that's purchased from other suppliers. This means that it's just a matter of mixing the Tesla silicon and graphite to create the anode before it's dumped into Tesla's dry battery electrode coating machine. The anode provides the biggest boost to range of any of the projects Tesla unveiled at Battery Day, with a 20% range increase, but curiously, only a 5% cost savings. This seems skewed until you realize that graphite in a typical battery cell is already half the cost and twice the energy density of the cathode material, which means that a huge change in the energy density of the anode by adding silicon only has a slight impact on cost. In order to hit the 20% range increase, Tesla would need to increase the silicon loading in the anode from the current 3% by weight to around 20 to 30% by weight, with the rest graphite. As we saw in the Cracking the Silicon Code video, it's not far-fetched to assume that Tesla's found the right combination of electrolyte, binder, and coating to make an anode with 20 to 30% silicon work. However, it may take a couple of years before we see a Tesla battery cell with 20 to 30% silicon by weight and all the benefits that brings. This is because 20 to 30% silicon is a massive leap from 3%, and pushing it too far, too fast would be high risk. I'm expecting less than 10% silicon in the current 4680 cell coming off the line at Kato Road. I'm basing this off Elon's comments that the cells are currently at around 300 watt-hours per kilogram. Besides energy density, increasing the silicon content of the anode should increase the charge rate of Tesla's battery cells. All indications are that 30% silicon can support an 80% charge in 5 minutes. But I don't expect to see supercharger rates that are that fast because there isn't a supercharger out there that can support that charge rate. To charge 80% of an 82 kilowatt-hour long-range Model Y pack in 5 minutes would require nearly 800 kilowatts of power, which is nearly 3 times the power of Tesla's current best 250 kilowatt V3 supercharger. For a much larger pack, such as the roughly 180 to 200 kilowatt-hour pack I expect for the long-range Cybertruck, it would require 2 megawatts of power for a 5-minute charge. Clearly, the potential charge rate of Tesla's vehicles in the near future will far exceed the ability of superchargers to deliver that power. Let's take a look at what we can reasonably expect in the next few years. A long-range Model 3 with 30% silicon should be able to charge from 0 to 80% in 17 minutes instead of 27 minutes, or nearly 40% faster. Again, I don't expect the 4680 cells currently being produced to hit these charge rates. Regardless, charge rates across Tesla's entire lineup should improve in the next few years as more silicon is added by both Tesla and Panasonic. As a final note on silicon, some people were wondering if Tesla could use high loadings of silicon in LFP or lithium iron phosphate batteries. This all depends on the cycle life of Tesla silicon. If Tesla silicon doesn't support the extremely high cycle life that LFP does, it would artificially limit battery life, which is LFP's greatest strength outside of cost. Even if Tesla achieved high silicon loadings at high cycle life, it's unlikely we'd see an LFP vehicle achieving greater than 300 miles of range before 2025. Before we move on to the battery factory, let's do another recap and also cover off a few odds and ends. Most of the 12% cost savings in Tesla's cathode will be from manufacturing in-house with an advanced cathode production process that uses pure nickel powder with near 100% yield that produces no toxic wastewater. Tesla silicon will provide more than just a range increase. It will enable fast charging. This will be gradual and occur over a few years, but it'll be noticeable. It won't take long for superchargers to become the bottleneck for fast charging. This will be true for both battery cells coming out of Giga Nevada and Tesla's 4680 production lines. As for the odds and ends, there are several inputs into the battery factory besides the cathode and anode materials, such as aluminum, graphite, copper, electrolyte, and plastic for the separator. These materials were notably absent from the presentation. Tesla focused on the materials that go into the cathode and anode because combined, they make up 65% of the cost of battery cells and 50% of the cost of battery packs. And most of that is the cathode. This is why Tesla's pushing upstream the hardest on the cathode to vertically integrate. Attacking the cost structure of the cathode helps lower the cost of the most expensive materials that go into the battery. Material cost is especially important for Tesla because as manufacturing a product scales, the cost of producing the product always approaches the material cost. The 4680 line is capable of 7 times the output of conventional battery cell production lines, so it won't be long before a battery line of that output reaches the material cost and Tesla hits the price floor. By reducing the cathode material cost, Tesla is extending the runway for cost reductions. Let's move on to localization. By moving lithium mining, lithium production, cathode production, and silicon production in-house, it will allow Tesla to localize and secure their supply chain. This is important for 3 reasons. First, it will allow Tesla to reorient the supply chain away from China's battery materials monopoly. Second, it will also decrease logistics and the associated carbon emissions. Third, it will remove blind spots in Tesla's supply chain and reduce issues with third-party suppliers. That's fewer headaches for Tesla in the coming years when they hit the steepest part of the electric vehicle adoption curve. You may have noticed that as we move further downstream, we move closer to innovations that we expect to see closer to the present. The lithium mine is probably more than 5 years away, the hydroxide plant is 18 months away, and the cathode plant is probably less than a year away. Tesla will expand their sphere of mastery to adjacent processes one at a time, allowing them to maintain line of sight. Now we get to the present, where Tesla is ramping production of the 4680 battery cell. This is our cue to move on to the meat of the Battery Day presentation, the battery cell factory. The dry battery electrode line was the most important technology Tesla unveiled at Battery Day. This is because the dry battery electrode has the most direct impact on Tesla's goal of accelerating the world's transition to sustainable energy of anything that was unveiled at Battery Day. The dry battery electrode, or DBE, is what allows Tesla to accelerate the speed of their lines by 7 times. That 7 times output increase at the front of the line means Tesla would have had to redesign the entire battery factory to accommodate. DBE isn't just difficult, it's extraordinarily difficult. Maxwell Technologies was working on the technology for a decade, and there are several other companies also working on it. Maxwell was the first to build something commercially viable, and Tesla acquired them and accelerated the development. I expect in a few years, other companies will start announcing factories that use DBE or similar technologies for the mid-2020s, but that's just a hunch. This brings us to Panasonic and LG's claims that they'll be producing 4680 battery cells within the next couple of years. We can kill 2 birds with 1 stone by discussing the key points of Tesla's cell design and what Panasonic and LG might adopt. First, 4680 is only a form factor, 46 by 80 millimeters. What's more important is everything that goes into that cell, which includes the tabless electrode, the cobalt-free high-nickel cathode material, Tesla silicon, and DBE. As for the tabless electrode, my view is that the tabless electrode or something similar would be necessary for LG and Panasonic's battery cells. This is because a cell as large as the 4680 needs good thermal management. The tabless electrode provides good thermal management by creating a large chunk of copper on the bottom of the cell that wicks away heat through the core of the battery cell. An important side note here is that the tabless electrode doesn't increase the charge rate. Rather, it allows the 4680 cell to charge at the same rate as a 2170 cell without overheating. It's Tesla silicon that will actually increase the charge rate. The tabless electrode is difficult, but I think it's well within the wheelhouse of LG and Panasonic, especially if they get tips from Tesla. If LG and Panasonic want their battery cells to work with Tesla's battery packs, Tesla must provide them with information on how the 4680 battery cells are wired and the exact dimensions. I'm assuming Tesla's provided them with all of this information because it's in Tesla's best interest to have more suppliers of these cells. As for the chemistry, I'd be surprised if either Panasonic or LG used Tesla's cobalt-free cathode recipe or Tesla silicon, but it's not out of the realm of possibility. Both the cathode and anode are tied up with a lot of other intellectual property and trade secrets that Tesla might not let go of so easily. DBE is another story altogether. It involves the crown jewel of Tesla's battery cell production line. It's not easily duplicated and would probably require Tesla to lend some of their best and brightest engineers out to other companies to show them how it's done. And this is while Tesla itself is trying to ramp their own DBE lines. It sounds like both LG and Panasonic had no plans for the 4680 battery cell until the day after Battery Day. If they plan on having these batteries at full-scale production within the next 2 years, it's doubtful they're brimming with new technology like DBE. It takes them a year just to set up a carbon copy of one of their existing lines and hit a decent yield rate. I'm guessing they'll have prototype 4680 lines running this year, but it may be another year or more after that before we see full-scale production at a high yield rate. There's a good chance that those cells will have a tabless electrode, a slim chance that they'll use Tesla's cathode and anode, and a very low chance those 4680 cells will use DBE. I haven't seen either LG or Panasonic indicate they have anything brewing with DBE, but they may have partnerships that I'm not aware of. As always, if you know something here I don't, let me know in the comments below. Let's take a closer look at the 4680. The 4680 cell design increases range by 16%, which is roughly equivalent to a 14% improvement in energy density. This is because increasing the energy density slightly reduces the weight of the vehicle, which compounds the impact of the energy density increase. This is because battery cells that weigh less mean a vehicle that weighs less, meaning the vehicle can go further with the same amount of energy. 7% of the 14% energy density increase is a result of increasing the size of the battery cell from Tesla's current 2170 battery cell to 4680. How? If the internal volume of the cell increases and the shell of the battery cell remains the same thickness, the energy density increases. This is because the shell is dead weight and the ratio of energy storing material to dead weight increases. Another 5% of the 14% energy density increase would actually come from reducing the resistance in the battery cell with the tabless electrode. Resistance is basically electrical friction that generates heat. Any energy being wasted as heat is energy not being used to propel the vehicle. The tabless electrode reduces resistance by shortening the path of the electricity to and from the active materials on the cathode and anode. Next, 2% of the 14% energy density increase was probably due to Maxwell's dry battery electrode. DBE allows for less binder to be used in the battery cell and also allows for a thicker cathode. A thicker cathode means increasing the ratio of active material versus inactive material like aluminum electrode foils, making it very easy to generate another 2% energy density increase. There are several other ways DBE can improve energy density, but a thicker cathode seems most likely. Let's tally up the energy density improvements. 7% from the size increase, 5% from reduced resistance, and 2% from improvements related to DBE adds up to 14%. With the range increase explained, let's look at the 14% cost reduction from cell design. This number is more slippery, but the main cause of the cost decrease would be the massive reduction in the number of cell cans, welds, and electrolyte fills for each vehicle. 500 to 1,000 of these 4680 cells will be used in each vehicle instead of 4,000 or so of the 2170 cell. This seriously uncorks the throughput of both the battery cell production line and pack assembly by reducing the number of actions by 75% or more. Before we move on to the structural battery, I'd like to point out one more detail on this stacking it up slide. The greatest reduction in cell cost is due to the cell factory. It will reduce the cost of batteries at the pack level by 18% and also accounts for nearly half of the 69% decrease in investment cost. DBE is what makes a lot of that possible. However, there's a supporting cast behind DBE, some silent stars that are often neglected. First is the end-to-end redesign of the battery cell production line by Tesla. Tesla touched on this briefly at Battery Day, but what I've seen in the subsequent videos released after Battery Day was thrilling. I've watched a lot of videos of production equipment, but the machinery we're seeing here is something altogether different. Everything we see here was precisely machined out of thick chunks of stainless steel. Not a penny was spared. I'd love to know the story of how this was built and designed. I'm picking up a lovely bouquet of heavy-duty American design and innovation, notes of precision German engineering, and maybe a hint of SpaceX alien technology to round out the body. Furthermore, it looks like there are no people on the cell line, and I'm hoping that it's fully managed through a control room. That is, full automation. The good thing about batteries is there are no situations where you need a flufferbot. Battery manufacturing, unlike some parts of general assembly for vehicles, tends to lend itself to full automation. I don't know if it's been fully achieved in other battery cell lines or if Tesla has achieved it, but the level of automation looks promising from what Tesla has shown in their teaser videos. Next, as a point of interest, I suggested in a previous video that Tesla may have found a way to do the DBE coating process without using some type of trim device like we see here. I think that was wrong. I've since confirmed with someone who works with the technology at a lab scale that the scraps can be reused. This is huge. It means that Tesla won't need to recycle these scraps and that this part of the process may have a 100% yield rate. Tesla may still need recycling for battery cells that fail quality control later in the process, but the trim is well positioned from a yield loss standpoint. Initially, I'm not sure who will be recycling battery cells that fail quality control or what process will be used. I'm hoping that Tesla's developing a pilot recycling process in-house to deal with cells that fail quality control. Then, later in the decade, Tesla could not only recycle cells that failed quality control, but also batteries from end-of-life vehicles. Recycled battery material from end-of-life batteries could significantly reduce the cost of raw materials that go into Tesla's battery cells because it'll be cheaper to mine used batteries rather than building an actual mine. This is because batteries contain all the elements in one place and at high concentration. However, those cost impacts could be a decade away. I say this for two reasons. First, that's how long it'll be before we see recycled nickel from batteries in a high enough volume to affect the cell cost. Second, battery recycling is just starting to become profitable, but that varies depending on the chemistry and the process used. J.B. Straubel claims Redwood Materials is profitable on a unit basis, but not yet at a company level. I expect this will change in the next few years as large-scale, environmentally friendly, and higher-margin processes come online. Panasonic has partnered with Redwood Materials to recycle the waste from Giga Nevada. Tesla could follow suit in the near term, but in the longer term, I'd prefer to see them develop an in-house process because they'll already have the benefit of scale and a closed loop as vehicles return from the robotaxi fleet or lease. The last topic before we move on to the summary is the structural battery. This was the biggest surprise of Battery Day for me. In most vehicles, the battery pack adds weight. This is because the battery pack is a heavy steel enclosure that carries the batteries like fragile eggs. The batteries are not fragile, and as a group, they have the strength to deal with thousands of kilograms of compressive stress. The structural battery pack strips out the steel box and uses the battery as structure instead. This means the batteries serve two functions. They both store energy and replace some of the structure of the vehicle. To put it in simple terms, the pack weight usually carries a penalty. For example, the 247 watt-hour per kilogram cells that were previously being used in the Model 3 ended up with an energy density of about 160 watt-hours per kilogram at the pack level. With the structural battery, the energy density of the pack, after taking into account its effect on the vehicle structure, could actually have an energy density greater than 247 watt-hours per kilogram because the structural battery pack reduces the total mass of the vehicle. Or, as Elon said simply and cleanly, cell to structure has the effect of negative mass. My view is that the general layout of the structural battery pack will be coolant lines at the bottom and wiring at the top. This will all be bonded together in a sandwich of cells, epoxy, and two face sheets. That is, the electrical connections would be near the battery management system and vehicle wiring, and the thermally conductive copper negative on the bottom against the cooling plate. As for the 10% weight reduction that results in the 14% range increase, I think the 10% weight increase is at the vehicle level rather than at the pack level and would also include the gigacastings. This makes it difficult to tease out the exact weight savings of the pack alone, and I'm looking forward to a Sandy Monroe teardown to let us know where the weight has been cut. The castings for the Model Y will use the largest casting machines ever produced. Due to the new aluminum alloy Tesla has created in-house, these castings won't require heat treatment or coatings. Both heat treatments and coatings add a significant amount of cost to cast products, and it's a small miracle that Tesla's managed to develop an alloy that can do so many tricks at once. The gigacastings will allow Tesla to reduce the length of the vehicle manufacturing line by 20% by cutting 2/3 of the robots out of the body shop. Furthermore, every casting will come out micrometer precise. This is compared to the current stamped structures that are clumsy to weld into a consistent underbody, making the rest of the vehicle more difficult to assemble up from the underbody. Overall, the gigacastings will allow Tesla to ramp their production lines faster and cheaper while cranking out vehicles that have laser-like precision. It's now time to run through my thoughts on the implications of Battery Day, estimates, projections, and insights after working on the series for 9 months. At Battery Day, Tesla effectively announced that energy density, cost, and scalability are now solved problems. From my perspective, it's a matter of Tesla executing, and I have confidence they will. The next challenge is material supply. Tesla will be playing whack-a-mole with material supply issues as the battery material supply chain gets hit by a square wave of battery material demand that the mining and refining industries haven't prepared for. We'll come back to this in a moment. Although scale and cost are by far the most important targets, energy density is a technological edge, and I did make energy density predictions before Battery Day. Let's look at those. I predicted an energy density of at least 300 watt-hours per kilogram as a certainty, with a maximum of about 345 watt-hours per kilogram at very low likelihood within a year of Battery Day. What did we get? Elon's indicated on more than one occasion since Battery Day that Tesla is at just over 300 watt-hours per kilogram. Here's my thinking on why that sounds about right and why it isn't much more than 300 watt-hours per kilogram. Let's assume that before Battery Day, Tesla was getting about 247 watt-hours per kilogram at the cell level. Some people have claimed it was more, but I haven't seen any actual cell analysis to support this. Tesla claimed a 16% range increase from cell design and 4% from a new cathode material, which tallies up to a 20% range increase. As I said earlier, I don't think Tesla silicon is quite ready for prime time at the full 20% range increase. I do think they can easily get to a 6 to 10% range increase from silicon in the 4680 cells coming off the line right now at Kato Road. I'll lowball that and target a 6% range increase to be conservative. We won't count cell-to-vehicle integration because that's a pack level multiplier. Tally up the 20% from cell design and cathode and 6% from silicon, and it results in a 26% range increase. If we convert that to energy density, it's about a 23% improvement. Add 23% to 247 watt-hours per kilogram, and it feeds back 304 watt-hours per kilogram. I'd like to stress that I'm being purposefully conservative here. When Tesla does tack on the next 14% of range from silicon, they'll end up with a cell that has an energy density of around 333 watt-hours per kilogram. I view this as a minimum. If we take into account that Tesla's baseline may have been more like 260 watt-hours per kilogram instead of 247, Tesla may be able to hit 350 watt-hours per kilogram in the next 2 years at large scale. This would be a maximum. I feel like I nailed it here with my pre-Battery Day predictions videos. My predictions about form factor, cell-to-pack, DBE, tabless electrode, cobalt-free cathode, and line output were all fairly solid. I was happy to see that my main blind spot was that I severely underestimated Tesla's appetite for moving upstream. I did predict silicon in earlier videos, but left it out of later predictions because I didn't expect Tesla to move to a high loading of silicon within a year of Battery Day. Technically, they don't appear to have moved to a high silicon loading if their energy density is still around 300 watt-hours per kilogram. I do think I should have spent more time on silicon in my predictions videos, but that's not a disappointment. It was nice to have surprises on Battery Day that overshot my expectations. So surely, with all of this extra energy density, we'll see a massive spike in range. My view is that range will increase, but not drastically, because battery materials will be running lean for most raw materials in about 3 years. To cope, Tesla will continue to squeeze out incremental range improvements through efficiencies in software, hardware, and weight reductions, with the occasional 5% boost from a slight tweak in cell chemistry. This is to make the most out of every cell that they can get their hands on. As Elon said on Twitter in February, and I've been saying publicly since last year, I expect Tesla to shift their entire standard range lineup to LFP batteries. This is because iron is abundant compared to the nickel required for high energy density batteries used in long-range vehicles. However, LFP battery packs will be hard-pressed to hit 300 miles of range, and that number appears to include all the improvements from Battery Day. Most consumers in North America and Europe will likely go for vehicles that have a range of 300 miles or more. The fact that the robotaxi fleet will likely use LFP will help shift the balance, but we don't know how much of Tesla's vehicle production will be devoted to the fleet. My view is that we're already seeing signs of belt tightening around nickel. Tesla could have increased the range of the new Model S far beyond the 412 miles of range by using a battery pack with the same kilowatt-hour rating as the former Model S, but it appears they didn't. While it's true that Tesla's three-pronged approach will take some of the sting out of the upcoming battery materials supply shortage, it has limits. If we take a rough guess that 50% of Tesla's vehicles will have an LFP pack, this still leaves the other half nickel. Tesla's nickel plus manganese chemistry will allow Tesla to increase the output of nickel-based batteries by 50%, but that will be blunted by the huge amount of nickel cells going into the Cybertruck and Semi. In terms of cost, I expected $88 per kilowatt hour at the pack level within a year of Battery Day, which would be September 2021. The gray and red lines in this image were from Tesla. My assumption is that the intervals are $20 per kilowatt hour. If that's true, and this is an accurate representation of Tesla's expectations, the gray line follows Sandy Monroe's cost analysis quite well, which was $110 per kilowatt hour in 2020 and $135 per kilowatt hour in early 2018 on what was likely an early production 2017 Model 3. As a side note, Sandy has come out with some updated cost estimates, but I don't know enough about those estimates to get into them in this video. I stated repeatedly in my $88 prediction that I was using the most conservative assumptions. If the assumptions were all pushed to the aggressive side, it would have put my prediction at about $80 per kilowatt hour at the pack level. In other words, in terms of cost, I was too aggressive in the short term and not aggressive enough in the long term. The 10 gigawatt hour line at Kato Road in Fremont, California is probably just hitting the exponential part of the S-curve right now in June 2021. The red line breaks below $90 per kilowatt hour in the second half of 2022. Which means costs may not start plummeting until production hits scale with the Big Daddy 20 gigawatt hour lines that'll be rolled out in 2022. The cell costs will continue to plummet heading towards 2025 as processes are embedded at the cell factories, cathode plant, and hydroxide plant, and as Tesla realizes the scale benefits of having the largest battery factories in the world. If the $20 increment I suggest on this graph is correct, Tesla might hit $50 per kilowatt hour around 2025. That seems super aggressive for nickel, but possible, and with LFP, it definitely seems doable. Let's get into some speculation about Tesla's upcoming compact vehicle, which we'll call the Model 2 to keep things simple. If Tesla wants a good-sized margin on the Model 2, they'll need a pack cost of at most $90 per kilowatt hour. That's not an exact figure, but rather, it's in line with a few different estimates I've seen. If my $90 assumption is correct, and this image is correct, the door is open for the Model 2 starting in late 2022. I'm expecting it in late 2023 because in 2022, Tesla will be devoting all their cells to ramping the Cybertruck, Model Y, Semi, and possibly Roadster. According to a German teardown, at scale, the Model 3 costs about $28,000 to build. Let's say the Model 2 is 20% smaller in terms of mass. If we assume mass and cost have a linear relationship, it would mean a Model 2 that's 20% smaller than the Model 3 would cost $22,500 to build. The German teardown indicated that the battery was 40% of the vehicle production cost. Apply 40% to $22,500 and the result is a $9,000 battery pack for the Model 2. Tesla's 2018 pack cost was estimated at $135 per kilowatt hour. If we assume the pack cost could be cut by at least half from $135 per kilowatt hour in 2018 to around $67 per kilowatt hour in late 2023, the result would be a $4,500 cost savings for the Model 2 battery pack. That $4,500 drop in battery pack cost from a total vehicle cost of $22,500 would net an $18,000 production cost for the Model 2 when it hits scale in 2024. If the Model 2 base price was $25,000, this would allow for a 28% margin. Again, this is back of the napkin math. I feel like I'm not being overly aggressive or sandbagging here, but I definitely see the cost reducing further in the late 2020s. As a side note, I ran similar numbers on the Model 3 and arrived at a production cost of $20,000 in 2025. Needless to say, with these numbers, Tesla could price the Model 3 well below the cost of ICE vehicles and demand would be insane. But I think demand will keep prices high in the mid-2020s, and the price of the Model 3 will remain steady with up to a 50% margin. The catch here is that this is only if the Model 3 was updated with Tesla's full suite of efficiency and cost improvements. Let's get into some speculation about the 4680 production ramp. Just after Battery Day, I created this image. It's loosely based on what Elon said at Battery Day. I didn't speak directly to the image in any of the videos, but it was collateral. And even when I'm making collateral for the channel, I try to put a lot of thought into the information that's displayed. However, until I script an idea, I haven't fully thought it out, and that's certainly the case here. What I hadn't taken into account was that if the final version of the line at Kato Road in Fremont is created in spring of 2021, Tesla would want to fully ramp or nearly fully ramp the Kato Road line before making the 20 gigawatt-hour version at Giga Berlin and Austin. This is because you don't want to start making copies of a pilot line that hasn't proven itself. I actually suggested in prior videos that Tesla would want to have a fully operational pilot line before ramping the next line, but I failed to factor that in here. What we see here with regards to 4680 production lines is what I expect the original plan was, but Berlin and Austin might actually end up swapping places. Giga Austin appears to be passing Giga Berlin in vehicle production, and Tesla might reroute the machinery for Berlin to Austin. With that said, we'll continue under the assumption that Berlin will finish first, for two reasons. First, Elon said in the Q1 earnings call that most of the equipment was ordered for Berlin and much of the equipment was ordered for Austin. Second, some of Tesla's major suppliers for the 4680 line, such as Grohmann Engineering, are based in Germany. Let's get into the timeline. The production halls for the first 4680 production lines break ground in Berlin and Austin in Q3. Equipment installation would begin in Berlin in Q4 2021 and Austin in Q1 of 2022, with 100 gigawatt hours of capacity at each site. Berlin would begin the production ramp of the 4680 in February of 2022, and Austin would begin by May of 2022. By the end of Q2 of 2022, Berlin would need to be near full production of its 100 gigawatt-hour run rate, providing for a total production of 60 gigawatt-hours by the end of the year. Austin would trail a few months behind, which would mean 2 to 3 months less of production at the 100 gigawatt-hour run rate, resulting in 40 gigawatt-hours produced for the year. This brings us to Elon's comment in April of 2021 in the Q1 earnings call that volume production would be reached in 12 to 18 months. It would take Berlin a couple of months from the start of production in February to start producing usable cells at any significant volume, which is roughly April of 2022. That's 12 months. It would take another 3 months for Berlin to hit capacity, and Austin could be 3 months behind, hitting capacity by September 2022, which is 18 months. This gives us a range of 12 to 18 months. As a side note on Elon's comment about 12 to 18 months to volume production, many people confused pilot production with volume production. even though the 10 gigawatt-hour Kato Road facility is volume production by conventional standards, it's 1/10 the production capacity being installed in each Berlin and Austin, so it's not volume production by Tesla standards. In the Q1 earnings call, Elon also said the 4680 cells weren't quite reliable enough to go into vehicles yet. This is to be expected. Before Battery Day, I said it would take 6 months for a pilot line to hit steady state. If we assume that Tesla probably only just finalized the pilot line in the past few months, that puts a 10 gigawatt-hour run rate between September and November of 2021. The natural progression of a production line is to get the line working at low speed, then ratchet up the speed. Along the way, quality is sacrificed. Once the target speed is reached, the final 2 steps are to increase quality, which in the case of batteries means reliability, and to hit the cost targets. In other words, as Elon said in the Q1 earnings call, Tesla is now focused on the nitty-gritty details of getting the pilot line commissioned, and they're getting close to shipping these cells in vehicles. Drew followed up by saying that the yield trajectory aligns with their internal cost projections. In other words, this is actually really good news, not bad news. We've already seen this play out in Tesla's vehicle production lines, so it shouldn't come as a shock. For example, when Tesla was ramping the Model 3, they were encountering quality issues like paint peeling and panel gaps. Eventually, those were ironed out when the lines hit steady state. This is the normal process for ramping a production line. Increased speed reduces quality, then those quality issues are resolved at the new higher production rate. Wash, rinse, and repeat. There's always a balance between quality and throughput when ramping a production line. Vehicles with some panel gaps and minor paint issues are still acceptable to sell, and so Tesla continued to sell them. Batteries require 100% quality. If a battery cell fails, it means a shorter battery life and safety issues. This means Tesla needs to fully ramp the battery cell production line at high quality before putting those cells into vehicles. You can't just take the first cells off the line and put them in a product the way you can take the first vehicles off the line and sell them. It's not a bad thing, it's just the nature of battery cell production, and re-emphasizes the point that reliability issues shouldn't be ringing alarm bells just yet. This doesn't mean that there should be no concerns, and I'm certainly looking for an update in the next earnings call. But so far, we haven't seen anything out of the ordinary for a production ramp. Regardless, even partial production from the Kato 4680 line would be enough for the production ramp of the Berlin and Austin Model Ys. Austin won't need 4680 cells in serious volume until the end of 2021 at the earliest, and Berlin until early 2022. This gives Tesla a good 4 to 6 months from Elon's comment in the Q1 earnings call to work out the reliability kinks in the 4680 cell line for the start of production at Austin. Note that I'm saying production here rather than deliveries, which will lag by 2 to 3 months. Let's take another view on this, but rather than focusing on the progress of the full-scale 4680 lines in Austin and Berlin, we'll view it from the lens of Kato Road. This is because Kato Road will be Tesla's sole source of 4680s for at least the next 6 to 9 months. But they'll also be ramping multiple vehicle production lines that will probably require 4680 cells. The Kato Road line could supply roughly 5 gigawatt hours of cells on an annualized basis by the end of Q3 of this year, and nearly 10 gigawatt hours by the end of the year. A 10 gigawatt hour run rate should be enough for about 150,000 Model Ys per year with Tesla's next generation Model Y platform. But it also depends on the size of the packs and the mix of long range versus standard range plus. This would be far more cells than Berlin or Austin would need in the first 6 months of their ramps, because it will be Tesla's first implementations of their next generation production system and new factories and workforces. Shanghai usually achieves a 150,000 vehicle production run rate within 6 months, and I expect Austin and Berlin to take at least that long. I estimate production start dates of late Q3 and Q4 for Austin and Berlin, respectively. In other words, Austin and Berlin combined wouldn't be using that many cells until Q1 at the earliest. This works out well for the Semi. In Q3 and Q4 of this year, there should be quite a large number of cells available if Kato is hitting a 5 GWh run rate in late Q3. However, that may not last long. By Q2 of 2022, the Austin Y will probably be using up to half of the output of Kato, and the Berlin Y will be using up to a quarter of the output. This means that Kato Road should keep Austin and Berlin fed until the end of Q1 of 2022, but after that they'll start becoming cell-starved. We also have to take into account the Austin Cybertruck, which will be the first truly novel vehicle production system in a century and an entirely new platform for Tesla. That will certainly carry a learning curve, and I'm prepared for a slow initial production ramp. I expect production start for the Cybertruck in Q1 of 2022, which means there won't be much cell pressure from the Cybertruck on the Kato cell supply until Q2 of 2022. This all points to a bottleneck for the 4680 cells from Kato Road in late Q1 or early Q2 of 2022. However, if we assume the Berlin 4680 factory can start producing even a fraction of its 100 GWh capacity in Q2 of 2022, then the bottleneck could be broken in relatively short order. Berlin will then have plenty of cells to continue the ramp for the Berlin Model Y, and possibly enough cells to provide support for the Austin Y, Austin Cybertruck, and the Semi. Additionally, when the Berlin 4680 lines kick into gear, the Kato Road line can fully devote its output to the Austin Y and Cybertruck. Finally, in late Q2 of 2022, I hope to see the Austin 4680 lines begin supporting the Austin Y, Cybertruck, and Semi. Originally, this timeline assumed that there would be a Plaid Plus Model S that would start absorbing cells from the Kato 4680 line in late 2022. But that's now changed. Elon just dropped a bomb this week stating that the Plaid Plus Model S is canceled. I haven't had time to process this new information, and it would take another video to explain why I think Tesla made this choice. Regardless, in late 2022, when Berlin and Austin are fully supported by their local 4680 lines, the cells from Kato Road in late 2022 will need to go into vehicles somewhere. Here's what I'd like to see happen with those cells. Kato could fully devote its output to Fremont, and those cells could be used for two things. First, I'd like to see the Roadster in production in late 2022. Which will probably only be produced in the thousands rather than the tens of thousands. This means the Roadster would use less than a gigawatt-hour of cells. Next, I'd like to see Tesla begin cutting the Fremont Model Y over to the 4680 so that all North American Model Ys use the 4680 cell. On that note, it's worth calling out here that I was wrong about the Model Y in North America using the 2170. Elon has confirmed that the Austin Y will use the 4680. This leaves me with a concern that Tesla will be using two different technology platforms for the same vehicle in the US, which would cause frustration for some potential buyers. However, I don't think it will dissuade enough buyers to impact Tesla's demand. Furthermore, if Tesla does use the Kato 4680 cells to cut Fremont Ys over to the 4680 architecture, the situation will only be temporary. Again, this is all speculation. The purpose is to look at how everything could play out if everything Elon has said is true. It's indicative rather than prescriptive. As I said earlier, we might see the Austin and Berlin 4680 production lines swap places, with Austin delivering first. According to Jeff Roberts, the battery cell line has already broken ground in Austin, and we haven't seen any evidence of groundbreaking in Berlin. If that's the case, it would be a big shakeup, but if it does happen, Tesla can ship the cells to where and when they need them on a temporary basis. On Battery Day, Tesla claimed they'd hit 100 gigawatt-hours of cells produced in 2022, and I've just explained how they might do that. Can Tesla actually do this, and what would they do with all of those cells? As I said in prior videos, this number left me gobsmacked and it seemed over the top. I questioned whether this was total cells produced, installed capacity, or run rate. Elon appeared to reaffirm the 100 gigawatt-hours of cells produced in the Q4 2020 earnings call.
The number to think about, focus on, is like we've got 100 gigawatt hour total Tesla cells produced in 2022. But we are installing capacity in 2022 for 200 gigawatt hours a year, and we think probably we should be able to achieve 50% of targeted design capacity in 2022.
That's a hell of a lot of cells, and even if they only hit 50 gigawatt hours produced, it'll be an achievement. I expect more than 50 gigawatt hours produced, but less than 100 gigawatt hours. Either way, the trickle of 4680 cells will turn into a deluge. What does Tesla need that many cells for? The Semi will be able to soak up at least 30 gigawatt hours of cell production at a rate of just 50,000 vehicles a year. The higher trim versions of the Cybertruck will use roughly 10 gigawatt hours of cells per year for 50,000 vehicles. This is compared to about 4 gigawatt hours of cells to make 50,000 vehicles for the Model Y. In other words, the Semi and Cybertruck in Austin will be like a Sarlacc pit for the battery cells, eventually swallowing up several hundred gigawatt hours of cell production without breaking a sweat. It's unclear at this point what all the cells at Berlin will be used for, but initially some could be shipped to Austin while Berlin ramps new vehicle lines. What about Tesla's cell supply from Panasonic? First, at Battery Day, Tesla indicated that they still plan to increase production in Nevada to 150 gigawatt hours. The production capacity of Giga Nevada as of 2020 was around 33 to 34 gigawatt hours. Late last year and early this year, Panasonic upgraded the lines to 35 gigawatt hours. Next year, they intend to install one line, bringing production up to 38 to 39 gigawatt hours. In my view, this is exciting for energy storage. If Tesla's newer vehicles are using the 4680, all new production at Panasonic could be diverted to energy storage, and we should start to see the energy storage business really come into its own. Second, Elon and Drew advised in the Q1 earnings call that Tesla has asked their suppliers to double production in 2022. Panasonic Energy North America doesn't appear to have plans for this, and it seems unlikely that Panasonic would build the 2170 capacity in Japan, where the 18650 cells are made. Panasonic is expanding 18650 production in Japan, but those cells may not necessarily be for Tesla. Despite the 18650 being used in the Model S and X, Tesla probably isn't seeking a larger supply of these cells. Based on that information, it appears, at least at the moment, that Panasonic won't be doubling cell capacity to Tesla in 2022. This could very well change, and I do expect LG and CATL will double cell supply in China in 2022 without any issues. My guess is that Panasonic and Tesla still plan to expand at Giga Nevada, but they're waiting until Panasonic can install 4680 lines, which will be prototyped in Japan in 2022. This would mean full-scale 4680 production from Panasonic in Nevada in 2023. What about the 18650 cells produced in Japan for the Model S and X? Previously, the capacity of the 18650 plant in Japan was 10 gigawatt hours. However, after yield losses, that would have been just over 9 gigawatt hours, or enough for 90,000 Model S and X vehicles. In previous quarterly reports, Tesla stated that they had a production capacity of 90,000 vehicles, which matches the output of 18650s from Japan. Elon confirmed in the Q4 2020 earnings call that the new Model S is using an 18650 with an advanced chemistry. This advanced chemistry probably has 5% more energy density, and the new Model S and X are probably using fewer cells because they have so many energy efficiencies. This means the 18650 line in Japan can now probably stretch to 100,000 vehicles. In alignment with this, in the Q1 quarterly report, Tesla updated their guidance to 100,000 vehicles. My view is that this isn't coincidence, and that Fremont is now able to scale to 100,000 vehicles due to increased 18650 production in Japan and fewer 18650s required per vehicle. On screen is a summary of my best guess of Tesla's cell consumption in 2022 from all sources. In my view, 225 gigawatt hours is overly aggressive, 200 is realistic, and 175 is pessimistic. Things will again change drastically in 2023, and I won't make any assumptions that deep into the future. For the next 2 years, getting the right cells into the right vehicles at the right times will be like a massive game of Tetris. On screen is a deeper look into the future, but at lower fidelity. In the left panel is terawatt hours of cell consumption from all sources in blue. There's also an orange line. The orange line in the left panel doesn't follow the terawatt hour labels on the y-axis. It's a direct overlay of the millions of vehicles produced from the right-hand panel. I've done this to keep the graphs from being overly cluttered and make a point about the slope of the lines. The blue line more than doubles in 2022, nearly doubles in 2023, grows by 50% in 2024, and then slows to around 25% in 2025 and 2026 before going gangbusters again. Why am I bearish around 2025 to 2026? It takes 2 years to build a battery factory and 7 years to build a mine. This means the mining industry usually lags 5 years behind cell production. Until 2020, there was a glut of battery materials. That glut of battery materials is turning into a shortage in 2021, and the situation will continue to degrade over the next several years. Worse, there are no new super projects coming online in the early 2020s to feed the battery cell production boom. This sounds really bad for Tesla. However, from my perspective, it's still very bullish for 2 reasons. First, I'm not saying growth will stop, but rather that the growth may not be as fast in 2025 to 2026. Second, 2 times cell production growth for the next 3 years, with 25 to 33% growth for the following 2, is still, on average, more than 65% compound annual growth. I see the supply chain issues easing after 2026 for 2 reasons. First, I believe that market forces are kicking into gear now because miners have recognized that electric vehicles are now an inevitability rather than a speculative risk. I'm guessing it will take 5 years to develop new mines, which is actually very fast. This leads us to the second point, which is that I'm hoping that governments will jump in and start clearing red tape. Permitting and construction of mines will ultimately be what slows growth, and that's where governments can help most. Although incentives for EVs are a positive sign and signal to the market, they're primarily a demand lever, and there's already plenty of EV demand. The bottleneck now has shifted to supply. What companies like Tesla need is red tape to be cleared to support exponential growth. The upcoming battery material supply issues are common knowledge to those in the industry. Benchmark Minerals, RK Equity, Bloomberg, and others are all saying the same thing. A materials bottleneck is coming in the next 1 to 3 years, and there doesn't appear to be a solution in sight. As a side note, it's not just the active materials that can run short. It's things like the copper for the current collector and the metals for the electric motors. Yes, Elon has said several times that there's plenty of lithium and iron for LFP batteries. From a raw materials perspective, that is true. From a production standpoint, iron is nearly infinitely available. Lithium, on the other hand, may hit some production constraints, especially in the mid-2020s. That doesn't mean we run out of lithium. It simply means that demand may ramp faster than production scales in the mid to late 2020s. Tesla will have a hydroxide plant or plants, but they'll also need raw materials to feed them. It's also worth taking into account that a large portion of Tesla's vehicle fleet will require nickel, which is severely constrained in terms of both raw material supply and production. I'll do a video on this eventually to drive home the point. There are a lot of misconceptions out there on nickel. Overall, I'd love to be wrong on a material shortage, but I'd rather make accommodations for this in my forward-looking view, if for no other reason than to take into account inevitable black swan events like COVID, ships blocking the Suez Canal, chip shortages, or maybe something in the future like China invading Taiwan or escalation of trade wars. Finally, the orange line for vehicle production. In 2023 and 2024, I show gigawatt hours of cell supply exceeding the growth of vehicle production. This is because the Semi will require roughly 6 times the number of cells as the average Model Y. If the Semi hits any kind of serious volume, which I expect it will be a sponge for cells. As we discussed earlier, the Cybertruck will also weigh in heavily here. Overall, this means that Tesla will be producing 1/3 to 1/6 the number of vehicles with the same number of gigawatt hours at Giga Texas versus Fremont, Berlin, and Shanghai. Those vehicles will, however, be much higher cost with a greater margin in absolute dollars. In the mid-2020s, unlike cell supply, vehicle production doesn't miss a beat. Why? Tesla will launch one or more low-cost, super high-volume, compact commuter vehicles. These vehicles will be smaller, reap the gains from all Tesla's efficiency innovations, and consumers will probably accept 250 miles of range in most cases. This may mean an average pack size of around 50 kilowatt hours, possibly less, which will result in at least 50% more vehicles per gigawatt hour of cell production than a Model 3 or Y. Later in the 2020s, the market starts becoming saturated with electric vehicles, bending the exponential curve of vehicle production into an S-curve. However, as the scale of Tesla energy storage becomes a more significant part of their business, it offsets the attenuation of vehicle growth because the energy storage market is just as large as the vehicle market, if not larger. This will result in vehicle production continuing to grow linearly while the energy storage growth skyrockets, gobbling up cells. The end result is the delta between cell production in blue and vehicle production in orange we see in the left panel at the end of the decade. As always, this is my speculation. I've tried not to be overly aggressive or sandbag. Rather, I've tried to accurately synthesize everything I see occurring in raw materials to chemistry to product line in one image. Next up, people ask me daily about new technologies and technologies that might compete with what Tesla unveiled at Battery Day. I'm going to stop for a second here to answer all those questions with one sentence. My advice is that any startup that doesn't give any indication of cost per kilowatt hour and hasn't broken ground on a gigafactory are too early stage or too niche for serious investors. Percentage cost decreases are fine so long as we know what the benchmark is. This allows us to know whether the company is comparing apples to apples. If a company can't pass this basic test, then they're appealing to your imagination rather than good sense. What about solid state? A version of solid state is here now by Blue Solutions, and it's in commercial production for grid storage and large vehicles. If it met the cost and performance requirements of major auto OEMs, they'd be flocking to it. This tells us something important. The words solid state don't mean diddly if it doesn't meet the needs of a specific use case. Solid state's day will come, but lithium-ion is constantly improving in every dimension, which makes it a moving target. Let's review all the technologies presented at Battery Day in terms of innovation. The 4680 form factor isn't a technology in and of itself, it's just a form factor. There are positive and negatives to every form factor. I think Tesla stuck with cylindrical because it makes sense for the structural battery pack and because cylindrical cells lend themselves to continuous motion. What makes the large cylinder of the 4680 possible is the tabless electrode. The tabless electrode is very difficult, especially for a company that's never produced a battery cell. Now that they've figured it out, I expect they'll share the design with their partners and it will eventually become widespread. The dry battery electrode is difficult as hell. Many experts think Tesla is bluffing with DBE and aren't expecting it for another 3 to 5 years. If Tesla can pull it off, it'll be a coup. The dry battery electrode process cuts out one of the largest, most toxic, and most energy-intensive parts of the battery factory, which is the drying lines. Cutting that out reduces the footprint and energy consumption of electrode coating by 90% while improving the performance of the battery cells themselves. Without the dry battery electrode, we wouldn't be seeing the 7 times line speed increase that Tesla is claiming. Throughput and cost are what battery factories need more than anything right now to decrease cost and accelerate the world's transition to sustainable energy. Tesla might even be able to push past the 7x line speed later this decade. Tesla Silicon appears to be ahead of the industry and might give Tesla a longer-term advantage compared to other implementations of silicon I've seen. I'd say it solidly puts Tesla 2 years ahead on silicon-doped anodes, and that lead might grow throughout the decade if the polymer coating allows Tesla to incorporate more silicon into its batteries more quickly. For example, if Tesla can hit 25% silicon by 2022, that would put them about 3 years ahead. If they can hit 50% silicon by 2025, that would put them about 5 years ahead. That's assuming this image is correct and there are no disruptions or announcements, and I expect there to be at least one or two. High nickel, cobalt-free cathodes appear to be about 3 to 5 years ahead of the rest of the industry, and I think we can thank Jeff Dahn for Tesla's advancement here. Tesla's batteries already use very little cobalt, but any amount of cobalt carries reputational risks. With that said, the cathode production process is what's more important here. Cathode production is the first step upstream of the battery factory. No other auto OEM appears to be seriously considering moving this far upstream. Tesla's cathode reactor allows Tesla to use pure nickel powder, which should eliminate a lot of stupidity in the supply chain. By stupidity, I mean toxic, redundant processes that are expensive. However, Tesla is going even further in building a lithium hydroxide plant, which right off the bat will allow them to access a lot more lithium and save them 33% on the cost of their lithium hydroxide. If Tesla's suppliers can't provide enough mined material to feed Tesla's hydroxide plants, and so long as red tape doesn't get in the way, Tesla will do exactly what they say they're going to do and get into mining. Lithium is one of the elements of least concern to Tesla, and the earliest we might expect them to start a mine, based on development time alone, would be 5 years. If they build the clay mine, I wouldn't be surprised if they build lithium hydroxide and cathode plants at the mine, if not a battery cell factory. Tesla's formation and aging process isn't novel, but it is cutting edge and will have advantages over anything else in the industry. This is because Tesla probably has their own custom electronics, and they have more data on their battery cells than anyone else. It will shrink the size of the battery factory and potentially improve the performance of the battery cells themselves. The gigacastings are a modern miracle. Tesla's new alloy combined with Hydra gigacasting machines is just peanut butter and jelly. I don't know how far ahead this puts Tesla because I don't know how difficult it is to develop another alloy that can do the same things. It's far outside my zone of competence. Finally, the structural battery pack. The structural battery pack bonds the 4680 cells into the pack in a way that has the cells pulling double duty. The cells are no longer carried like cargo. They become the structural floor pan of the vehicle, cutting out 200 kilograms of excess steel that would normally be adding cost and decreasing range. If we consider all the innovations Tesla unveiled at Battery Day as a whole and what they expect to deliver in the next 18 months, it puts them at minimum over 5 years ahead of any Western competition. Tesla's closest competition is VW. At Power Day, VW put forward claims that won't be delivered on until 2024 to 2025, and those claims notably didn't include going upstream of battery cell production. The innovation we saw at Battery Day isn't the end of the story, and I'm looking forward to sharing what I think Tesla's next innovations could be, because there are several more technologies that could be ready for commercialization by 2025. But for now, it's time to finally close the book on the Battery Day series. Thanks for going on this journey with me. It's the culmination of 9 months of research before Battery Day and 9 months of research after Battery Day. There's a lot more to come on Tesla, but I'll be shifting gears and covering QuantumScape in the next few videos in a series called QuantumScape, the Good, the Bad, and the Ugly. If you enjoyed this video, please consider supporting me on Patreon with the link at the end of the video, or snag something off the merch shelf below. I'm also active on Twitter and Reddit. You can find the details of those in the description, and I look forward to hearing from you. A special thanks to Vincent Pluvinage of 1D Materials, Matt Henderson, and Sean Michael Egan for your generous support of the channel, my YouTube members, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.